Hello and welcome to our video covering section 5.3 of your textbook. In this video, we will discuss the notion of an orthogonal transformation and then discuss the notion of the transpose and see how that relates to orthogonal transformations in matrices. All right, so let's just right off the bat get a definition on the board. What is an orthogonal transformation? What is an orthogonal matrix? So your book defines an orthogonal transformation as follows. It's a linear transformation from Rn to Rn, and such a transformation is called orthogonal if it preserves the length of vectors. And by that they mean if you have some vector x, the transformation is orthogonal, then the length of t of x is going to be equal to the length of x for every x in your domain. And then an orthogonal matrix is just the matrix representation of an orthogonal transformation. And so one thing that we're going to focus on a lot in this video is just saying, okay, well, if an orthogonal transformation preserves lengths, what can we say about what the matrix representation of that has to look like? And let's just say right away that we know that we're only talking about square matrices here, and that's just because by definition, we're talking about linear transformations from Rn to Rn. So it's not just enough to preserve length, it's got to be a transformation from Rn to Rn. Okay, but I think a natural question to ask right away is like, why are these matrices called orthogonal transformations? Which orthogonal just implies right angles all over the place. And but the definition is actually in terms of lengths, not angles. So what's going on? Hang on, we'll get to it. First, let's start with some examples of orthogonal transformations. And your classic one is rotation. Like rotation, you take a vector, you swing it around, it's going to stay on a circle. The length isn't going to change. So rotations are your prototypical example of an orthogonal transformation. And so the matrix for a rotation is going to be an orthogonal matrix. So now let's think about projections. Is, say, a projection onto a line in R2, is that an orthogonal transformation? Yeah, no way. One way to see this is that just any vector that is perpendicular to the line is going to get sent to 0. And yeah, that's going to change the length for a lot of perpendicular vectors. So no. And we saw in a previous video that projection almost always makes the length smaller. So no, projection, not an orthogonal transformation. However, reflections are. So remember, reflection is if you have x and you want to reflect across a line or a plane, you take x, you break it up into its parallel and perpendicular vectors, and then the reflection is the parallel plus the negative of the perpendicular vector. So that's the definition of a reflection, and this is an orthogonal transformation. And let's prove it. Let's prove that reflections don't change the length of the vector. Like geometrically, it seems clear, but let's prove it algebraically. So notice that by the Pythagorean theorem, we have that the reflection is the length of the reflection. This is actually the hypotenuse of a right triangle. And this is true even in higher dimensions because remember, by definition, x parallel is perpendicular to x perp. So, okay, by the Pythagorean theorem, we've got the hypotenuse is equal, the square of the hypotenuse is equal to the square of the legs. And then notice, all right, well, the length of negative x perp is going to be the same as the length of x perp. So haven't done much to change things there. But then these are the legs of the right triangle where x is the hypotenuse. So by the Pythagorean theorem again, we get that these two are squared equals the length of x squared. And so indeed, the reflection squared is the length of x squared. Reflection didn't change the length. Now, I want to spend some time on an important theorem that your book only casually mentions. Like, really, they just kind of shove it into the bottom of a table, and it was like, you deal with this. So I actually think this is pretty important. It's one of the things I think about when I think about orthogonal transformations, and so I want you to think about it too. We're going to spend some time on it. So orthogonal transformations preserve the dot product, and that is great. So by that I mean, if you have x dot y and t is an orthogonal transformation, then t of x dot t of y is equal to just x dot y. And I think on your exam, I think I gave you a problem, or maybe it's a practice exam. I asked, is this true in general? And you told me, no, that's not true in general. But it is true for orthogonal transformations. So, okay, let's prove this, because this is important, and it ends up getting used. It makes other proofs easier if you know this. So yeah, let's prove it. The way we're going to do it is we're going to say, okay, well, look, since t is an orthogonal transformation, definitely true that t of x plus y squared, the length of t of x plus y squared is equal to the length of x plus y squared, because t is orthogonal. It preserves the length. And now what we're going to do is we're going to do some calculations with this length squared. We're going to do some calculations with this length squared. We're going to set them equal to each other and see what we get. Okay, so let's start with the x plus y length squared. Well, by definition, all right, the square of the length is equal to the whatever is inside dotted with itself. And here we have x plus y dot x plus y. And now the dot product, you treat it like a normal product, you FOIL basically. And so you get that this is equal to x dot x plus 2x dot y, because the dot product is commutative, plus y dot y. And then x dot x is the length of x squared. Don't mess with 2x dot y. And then y dot y is going to be length of y squared. So okay, let's do something similar with t of x plus y. But first, we're going to use the fact that t is linear to say t of x plus y is t of x plus t of y. All right, but now we're off to the races. We'll do the exact same calculation. The length of this squared is tx plus ty dot tx plus ty, which is equal to, you do your foiling, tx dot tx plus 2tx dot ty plus ty dot ty. And then recognizing that tx dot tx is the length of tx squared, ty dot ty is the length of ty squared. Okay, now these two guys are equal, which means these two expressions are equal. But notice, since t is an orthogonal transformation, length of t of x squared has to be the same as length of x squared. Length of t of y squared has to be length of y squared. And so these cancel, and we're left with 2t of x dot t of y equals 2x dot y. Cancel the 2's. X dot y is t of x dot t of y. So there we go. Orthogonal transformations preserve the dot product. And we're going to pretty immediately put this to use. So why are orthogonal matrices called orthogonal? Well, it comes down to this really important notion that orthogonal transformations don't just preserve length, they preserve orthogonality. They preserve right angles. So that's what this theorem says. It says, all right, if you have an orthogonal transformation from Rn to Rn, then if the vectors v and w are orthogonal, then so are t of v and t of w. So it preserves right angles. And in fact, it preserves all angles, not just right angles. So that's really nice. And we see this because it preserves the dot product. So yeah, we'll give a little proof here. You may recall from Calc 3, or if you just read the book carefully, they recall this themselves in definition 5.1.12. But in any case, in Calc 3, you have that the dot product of x dot y equals the length of x times the length of y times cosine theta, where theta is the angle between x and y. And so similarly, we will do this for t of x dot t of y. That dot product is equal to the length of t of x times the length of t of y times cosine theta 2, or theta 2 is now the angle between t of x and t of y. And look, we just showed that the orthogonal transformation preserves the dot product and it preserves lengths. And so since x dot y is tx dot ty and length of x, length of y is length of tx, length of ty, we have that cosine of theta 1 has to equal cosine of theta 2. And that just means that in absolute value, they are the same. So cool. Okay, so here are other ways to think about orthogonal transformations and orthogonal matrices. So a linear transformation is orthogonal if and only if the vectors t, the transformations of e1, e2, en, so the transformations of our standard basis vectors, if that forms an orthonormal basis for our n. And in matrix land, this means an n by n matrix A is orthogonal if and only if its columns form an orthonormal basis of Rn. And this is the thing that you should remember about orthogonal transformations. Preserves length, yes. Preserves angles, yes. But when you're looking at a matrix and you're asked, is this orthogonal? Check, are the columns orthonormal? Is it n by n and are the columns orthonormal? And if so, then there you go. You've got yourself an orthogonal matrix. So that's the one you use to check. But okay, let's prove this part A, the theoretical version of this, which says, okay, it's an if and only if, so you have two directions here. So let's prove it. So let's prove the first direction, which assumes if, so you're assuming your transformation's orthogonal, show that the transformed basis vectors are orthonormal. Well, first, let's note that the standard basis vectors are already orthonormal themselves. And then, since t is an orthogonal transformation, the transformed vectors are also orthonormal because, okay, the lengths are preserved, so they started out unit length, they end up unit length, and we just saw, we just saw that orthogonal transformations also preserve right angles. So, okay, if these started out unit length and all in right angles with each other, they end up unit length and all right angles with each other. So that one is the easier direction. So now let's go the other way. If the transformed vectors are orthonormal, then the transformation itself was orthogonal. Okay, so all right, let's start by supposing that the transformed standard basis vectors are orthonormal. And now let's write some random vector x in terms of a linear combination of the standard basis vectors. So x1, e1 all the way to xn, en. And now let's consider the length of this random vector t of x. We'll square it, and hopefully we'll end up showing that this is the same as the length of x squared, thus proving that it preserves lengths and is orthogonal. Okay, because t is linear, we can, when we take t of x and make it t of x of this linear combination, we can pull out all of the coefficients and distribute over addition. So there we go. And now we say, all right, this has to be equal to this sum. Why? Pythagorean theorem. This is where we are using the fact that these basis vectors are by hypothesis orthonormal, or really we're using the fact that they're orthogonal here. So because they're all orthogonal, they have Pythagorean theorem says, all right, this is just generalized to more dimensions. But yeah, Pythagorean theorem says, okay, the length of the hypotenuse is the length of the sum of all of these legs. So okay, this is Pythagorean theorem. And then we're saying, all right, well, this is if you have some length 1 vector and you scale it, then the resulting vector has length of the scalar. And since we're squaring it, this has length x1, and then this has length x2, this has length xn, and then we're squaring them all. Okay, so we have x1 plus x2, x1 squared plus x2 squared plus all the way up to xn squared. And that, my friends, is just the square of the length of x. Okay, so there we go. We've got the thing that you think about now when you see a matrix and you want to check if it's orthogonal. You have your test. The columns have to form an orthonormal basis, and we've kind of proved why. Okay, let's move on to some properties of orthogonal matrices themselves. So not the transformations, but the matrices. So first, we'll say the product of two orthogonal matrices is orthogonal. So this should not be surprising. Basically, if you do a transformation that doesn't change the length, and then you do another transformation that doesn't change length, then neither of those then doing the one after the other, you haven't changed the length. If you want to be technical about it, you say, all right, AB of the vector x, well, that's by the associative property, A of the vector bx. Since A preserves length, A of bx has to have the same length as bx. Oh, but b preserves length, so bx has to have the same length as x. So abx has the same length as x. AB is orthogonal. And then we have this other property, which says that the inverse of an orthogonal matrix is orthogonal. And that, okay, once again, kind of if you think about it, this shouldn't be too surprising. If you have a transformation that doesn't change the length of anything, and then you undo it, you haven't changed the length when you went back either. If you want to be technical about it, you say, all right, well, the length of A inverse x, that's going to be the same as the length of A inverse x, because A preserves length. A is orthogonal. So, all right, these two have the same length. And then you realize, okay, well, A times A inverse is just the identity matrix, which just gives us x. So indeed, A inverse of x has the same length of x. And maybe some of you were worried that we're just assuming that all orthogonal transformations have inverses. And yeah, they totally do. And this comes from the fact that if it's an orthogonal transformation, and remember, like I said on the previous slide, that means its matrix, all of the columns are orthonormal. Well, if the columns are orthonormal, they're linearly independent. And if the columns are all linearly independent and it's an n by n matrix, then yeah, your matrix has full rank and its reduced row echelon form is the identity. It is invertible. So if you were worried, stop that. Actually, it's good to be worried, but hopefully you're not now. Okay, so let's move on to this idea of the transpose and see how that relates to orthogonal matrices. All right, the definition. The transpose of an n by m matrix A, denoted A raised to the t, is the m by n matrix. So n by m matrix A. Then the transpose, denoted AT, is the m by n matrix you get by quote unquote flipping A across its main diagonal. So let's see what I mean here. Suppose we have this matrix A, 1, 2, 3, 4, 5, 6, 7, 8, 9. Draw a line down its main diagonal and flip the entries across the diagonal. And by that I mean, okay, the diagonal itself is going to stay where it is, so the diagonal is going to stay 1, 5, 9. But then you're going to flip 2 and 4. So 2 and 4 get flipped, and now 2 is in the first column and 4 is in the first row, as opposed to being 4 in the first column and 2 in the first row. Similarly, 3 and 7 get flipped, and 6 and 8 get flipped. And this works for matrices that aren't square. So the main diagonal comes off the upper left corner and goes down. And now if you're flipping this, then okay, 2 and 7 are going to get flipped. 3 is going to go into add some dead space here, as is 9. And so what we're going to get is we're going to get a matrix that has 3 rows and 2 columns instead of 2 rows and 3 columns. So that will be the transform. And we can even do this with vectors. You got some column vector 1, 2, 3. Take that guy's transpose. It's the row vector 1, 2, 3. So I like thinking about it in this kind of way of just you flip across the main diagonal, but there are more technical ways to talk about this. One is that the ith row of A becomes the ith column of A transpose. So here the third row of A, 7, 8, 9, becomes the third column of A transpose, 7, 8, 9. Similarly here, 1, 2, 3, first row of B becomes the first column of B transpose, 1, 2, 3. You could also say it this way, that the jth column of A becomes the jth row. Oh, did I switch that up? Anyway, they're saying the same thing. The ith row of A becomes the ith column, or the jth column becomes the jth row. Or you could kind of just do this entry by saying, all right, the ijth entry of A becomes the jith entry of AT. So you say, okay, you go to row 3, column 2, that becomes the entry of row 2, column 3, which is exactly what's happening. So, okay, here's some just things that are true about the transpose that just are no fun to verify. Your book does some of them. These are just some properties that are I don't really memorize these, but just kind of know that they're there, and when you're working on problems, refer to this. I would say that these first two actually aren't too hard to see why they might be true. If you just did a few small examples, you would see right away, okay, yeah, you add the entries and then transpose, or transpose add the entries, you're going to get the same thing. And maybe it's even easier to see that scaling and then taking the transpose is the same as taking the transpose and then scaling. This one, part C, this is a real hassle, but your book does go through it. And, I guess it's interesting, kind of like the inverse, the transpose means you switch the order of A and B. This part D is actually interesting, and I do want you to spend some time thinking about this. So the rank of your matrix is the same as the rank of the transpose. So if you took the reduced row echelon form of either of these, you would get the same number of leading ones. Or alternative way to think about this is if you think about the dimension of the columns of A, that's going to be the same as the dimension of the columns of A transpose. So that's something worth thinking about, why that's true. And then this last one, yeah, I think your book proves it. So just again, keep that in mind. Kind of interesting. The transpose of the inverse, or the transpose of the inverse, is the inverse of the transpose. All right, I don't think I'm going to spend any more time on that. Let's get some more definitions under our belt. A square matrix is called symmetric if it's equal to its transpose. So in 2 by 2 case, all symmetric matrices are of the form A, B, B, C. And if you think about this with the flipping over the diagonal, so if you want to flip over the diagonal and have the exact same matrix, well, remember the diagonal entries don't change when you take the transpose. So it's just the flipping. And so if you flipping doesn't change anything, that means that the two things that got flipped had to be the same. So we have BB here. A square matrix is called skew symmetric if the matrix is equal to the negative of its transpose. And so again, if we're thinking just in 2 by 2 land, now, all right, B and B, if one is going to be, if A is the negative of its transpose, B, one of these has to be negative. So yeah, skew symmetric matrices all have the form one of these entries is B, the other entry is minus B, or vice versa. And then, yeah, I want you to think about, and I think I put this, I don't know if I put this in your pre-assignment. Think about why these entries are 0 here. And is that true for matrices of even bigger dimensions? Okay, so we're in the home stretch here. One thing to notice is that if V and W are two column vectors, then if we take the dot product of V and W, we can actually write this as the matrix product V transpose times W. So we can, this notion of transposes lets us write dot products as matrix products and vice versa. If we have matrix products, the vice versa is if the matrix product is a row times a column vector. So for example, if we have the vector 1, 2, 3 dotted 1, negative 1, 1, like if we calculate that, this is going to be 1 minus 2 plus 3, which is going to be 2. And then if we take this row vector times this column vector, well, remember when we were defining matrix multiplication, we were saying, oh, well, what you do is you take the row dotted with the column, and then you would also get 2. There's one minor caveat here, which is that technically a row vector times a column vector, like as matrix multiplication goes, this is actually the 1-by-1 matrix too, not a scalar technically, but I think you might believe me if I told you that there was that the scalars and the set of 1-by-1 matrices are isomorphic to each other as vector spaces. So, okay, forgive the slight equivocation here. But okay, that is gonna set up. I would say the real truth problem we're gonna drop here, and a very nice theorem to end on. So, a matrix is orthogonal if and only if it turns out that ATA is the identity matrix, which is another way of saying that the inverse of your matrix is the same as its transpose. And that is great because I think it is an objectively known truth that calculating inverses is terrible. So if calculating inverses comes down to just flipping entries, that's awesome. So let's see that this is true, because this, you can see why this might be handy. So okay, let's write our matrix A in terms of its column vectors, and then let's calculate A transpose times A. So A transpose takes the column vectors, turns them into row vectors, and now let's do this matrix multiplication. Well, if you do it, we've got the first row, the first entry of our matrix is going to be the first row dotted with first column dotted with the first row. The other entries, we'll see, the second entry in the first row is the first column. Oh my gosh. All right, it's getting late. Let's wrap this up. This is the first column dotted with the second row, and so forth. You can confirm that this is true. Now, let's look at the entries of this specifically. First, let's check out the diagonals. We've got v1.v1, v2.v2, all the way down to vn.vn. And notice that these diagonal entries are going to be 1 if and only if each vi is a unit vector. If vi had a different length, then this is just the square of the length of v1, square of the length of v2. Then its square is going to have a different length, different from 1. So, okay, these are a 1 if and only if each of these vectors is a unit vector. And then let's look at the off-diagonal entries. These off-diagonal entries are going to be 0 if and only if vi dot vj is 0 for all I not equal to j. So you got v2.v1 or v2.vn, vn.v1, all of these off-diagonal entries. If we want them all to be 0, then it has to be that their dot product is 0. And so that means that, this is going to be the identity matrix if and only if our original vectors were unit vectors that were orthogonal to each other, which means it was an orthogonal matrix. All right, let's call it a day.